Welcome back to another episode of Life's Ambition Podcast. Today we are joined by someone who looks beyond the stars. He comes from the world of astronomy and how it relates to our environment today. Without further ado, Doug Arion. So Doug, how are we doing, man?
I'm doing very well. It's great to meet you in person. I knew your parents and your grandmother, obviously, my cousin. So it's great to meet you in person now and to chat about really cool things.
Yeah, no, I'm very excited about it. As I mentioned, like before we hit the record button here, is physics throughout high school and college was always a subject that I struggled with, but I loved learning about it just because I think it's so cool. Just the aspects of where it applies to. It literally applies to everything. And obviously,
Right.
I had a conversation with your brother, Mitch. That was an amazing conversation. And, I just kind of love to dive right into it and understand, how'd you get into the physics world?
So a couple of things. Firstly, Mitch and I both grew up in a household where my dad fixed things and built things. So I was always interested in just stuff, right? Um, but I really got started because of this thing called the Sears catalog. The 1968 fall edition had a telescope in it, and it looked like a cool thing. And so I cut a deal that any general manager would be proud of. Your next three birthdays plus a player to be named later, kind of thing, to get this telescope. But my parents, being very education oriented, also said, if you're going to get that, then you have to go to the library and read the astronomy books. So I started getting interested in astronomy and physics because I got interested in a telescope. And so that's what really got me started. And that was, I was 11 years old in 1968. So it's
Wow.
been
So you knew what you wanted to do
most of my
early
life.
on,
Yeah, very early on, getting interested in that. So,
which I find to be such a new thing for people. Or, yeah, I would say it's more of a newer thing for people nowadays because there's so many careers and so many things that people are exposed to. It's hard for an individual going into college to decide what they want to do. And for you to figure out that at 11 is really impressive.
yeah,
And so
yeah.
when you advanced through your school career, was it just strictly astronomy, physics? Where can I find school? Or was it a different path that you took in terms of, I like these other subjects, but I'm just not sure.
So, I, again, I was always interested in physics and astronomy. It was definitely something I wanted to study, but I've always been interested in lots of different things. And so um, I was lucky that I happened to go to an elementary school and a junior high school that were very, very good. Um, I, like Mitch, attended the Bronx High School of Science, which is arguably the world's number one high school. I basically had a college education by the time I got out of high school with what they taught us. But then I went to Dartmouth as an undergrad, which is, a premier liberal arts college. And despite the fact that it was a liberal arts school, my physics prep was actually very good coming out of there. In addition to all the other things that I learned about it, it had more of a formative effect on me as a person than anything else, was this diversity of study in all these other areas. I think that has a lot to do with why I've been successful in what I've been doing, because I have a bigger context. I'm not just a pure do the science person. Um, so then from there, I went to graduate school and started working. But yeah, I've always been interested in lots of different things, but the physics and astronomy stuff has always been at the core of it. And now what I'm doing, the public science work that I'm doing now, is really a liberal arts version of that, in that I'm much more interested in the bigger picture connections of everything than the detailed science. I think the detailed science is very cool, but I think the connections to all the different aspects of existence and evolution and people and life and everything is way more interesting. And that's what I'm interested in, and that's what I'm doing now. But I think some of that was born out of the fact that I had more diverse interest and the education I had supported that.
Hmm. And what was that high school that you went to again? What was the
It's
name
called
of
the
that?
Bronx High School of Science. It's in the Bronx in New York. Um, it certainly was and probably is the premier science and technology high school in the world. So in addition to taking all the regular classes that you took in high school, we also had classes in experimental design and mechanical drawing and higher level courses. And I was on the math team. And so I had 2 years of calculus before I got out of high school. I'd had 2 years of calculus, analytic geometry, complex analysis, real analysis, high level math stuff, high level science stuff. And so, I mean, it was really great professional preparation. It was a terrific school, still is.
Yeah, that totally sets you up. That sets you up perfectly for university, especially when you're going to a school like Dartmouth, which is one of the Ivy League programs. That is extremely cool, and congratulations to that. Did you have to test into it coming out of middle
Yes.
school, or okay? And then was it just
Yeah.
like I don't want to say like an SAT exam where they test you on math, science, and reading, or like an ACT, but was it kind of like that?
It was kind of like that. Yeah. Yeah. Everybody convened at the school one Saturday, and you took this entrance exam, and so it was combined with your entrance exam and your school scores and stuff to get in. And it was a big school. I mean, mine was a class of close to 900. I mean, it was a good sized school, but
Holy cow!
you
Yeah,
realize the accomplishments of all my classmates. We just had our 50th reunion this spring, and to see the accomplishments of all my classmates, it's mind blowing.
that's awesome. Well, and I'd love to kind of flash forward a little bit. You talk about how you're in the public space right now, but you were also in the government sector for a lot of your different projects. Can you describe what it's like being a physicist in a governmental program?
So, briefly, I did my PhD research and degree at the University of Maryland. I was recruited from there to work for a company. To the time was called SAI, Science Applications Incorporated. It then became SAIC. It split into two companies, SAIC and Leidos. So if you've flown anywhere and you've gone through a Leidos detector, that's the company that makes those. I worked for them for close to 15 years, and all of our work was government contracting. So we did a lot of work, mostly for the Department of Defense. And my part of the company, the part of the company that I ran, was responsible for doing what we call nuclear effects tests. We were the people who took various pieces of important U.S. equipment underground in Nevada, exposed them to actual nuclear weapons, and validated that they would operate correctly. And we used that. We used simulators and all sorts of other machines to do that. But it was very important work. This is back in the 80s and 90s when there was a very serious concern about an exchange between the U.S. and the Soviet Union. So protecting our defense assets was very, very important, and we got to do that work. So that was the first part of my career before I went off and started teaching.
How do you stabilize nuclear elements to be able to test them on different devices or even transport it?
So remember, it's not nuclear material. So what we have is we'd have, for example, a piece of a satellite. Okay, a piece of a satellite that's going to fly. We take it down in a tunnel. It's wired up so it thinks it's flying, and there are data recorders recording how it's behaving. At the other end of this tunnel is an actual nuclear weapon, a very small one, but it's put down there, and it's set off. And the radiation from that then hits all the experiments. There'd be many, many of these tests done on one shot. And that data would be recorded. You would have, in fact, one of our sister divisions, the one I actually started in, would do the calculations to say, when it gets hit, this is what we expect. We expect this much electric current to be moving. We expect this kind of temperatures. And then we measure it and say, yes, it matches that. Then we know that it's going to meet the specification that has been given for the mission that it has.
Yeah, because I find this part to be so interesting just because I don't know much about it, but what kind of instruments do you use to measure like radioactive activity, nuclear activity, and all this kind of stuff?
So depending on what the effect is that you're looking for, you use different kinds of instruments to do that. So, for example, if we're actually measuring the X-rays and gamma rays that come out of the weapon, which was one of the things that we did, we used a technology that was developed by a colleague of mine, where you have some little metal plates um, to which you hook up a wire, and when the radiation hits those metal plates, electrons come off. So you get an electric current. So we can use those things. We use different materials and different filters in front of them to select out different X-ray energies. So you can measure what each X-ray energy does during the shot. So that was one of the things that we used. If we're testing a satellite system, so that was one of the first shots I worked on, you have actual little coils that are put around individual wires all over the satellite. So you can measure the electric current that's going through it. It's similar to a device that would measure the amount of electric current that's flowing through something in your house, but obviously very specialized. And we would record those signals, for example. Some of the experiments we worked on, we actually had a fiber optic going into it, and we bounced light off of some mirrors so we could measure how those mirrors distorted when they got hit by radiation. So we built a system to do that. There are little devices called strain gauges that measure how much something gets stretched. So we could put those on a structure to find out how it was going to bend, right? Radiation hits one side, it gets hotter, so it bends on that side and eventually cools and comes back. We could measure that. So those are examples of some of the kinds of things that we used. They were all custom made. We had to design most of this and put it in. It was very challenging work. Very proud of the work that my team did. I had unbelievable engineers and scientists and computer people who worked with us to do this. It's just the greatest team of people to make this happen.
Which is amazing. And I guess, what was public perception of, or even just your own circle or your group of friends or family thinking about it during the time? Because Cold War, big, so obviously weapons were being mass produced. What was public perception of the work that you were doing?
Certainly at the time, and again, this is the mid 1980s to early, to mid 1990s. There were serious concerns about what would happen in Eastern Europe, and so this work. And again, everything I did was on the defensive side. I've never worked on a weapon system. I don't build bombs. We're not there. We were to make sure that everything that we had would allow us to survive. I think had a pretty positive reception, because we're like, no, we want to make sure that our communication systems, our weapon systems, everything will still be there, and that's a great deterrent, because actually, when I've given talks about this, I've explained that in sports, actually, the most important thing is defense. When I taught at Carthage, I was also the hockey coach, and I impressed upon my players. I said, look, if we don't give any goals, we're guaranteed at worst a 0-0 tie, and that gives you a point in the standings. That's the worst that can happen. If you give up a goal, now you don't have anything. You get 0 points. You got to score 1 to at least get even, and you got to score 2 to actually win the game. So it's much better not to give up goals, right? You have to think of defense before offense. And that was true in our nuclear area too. We weren't here to say, well, we're going to have more bombs than the other side. We never have. We've never had more than anybody else. But we were defensively so good. I mean, it's the famous song, I forget who sang it, hit me with your best shot. It's kind of like, we've designed everything that you can hit us with your best shot, but we're still going to be here. And that makes it much less likely that somebody's going to attack you, right? So
yeah,
that was very effective.
Yeah, and I guess like where I was thinking in my head is, I think about events like Chernobyl. I know that happened a little bit later when nuclear reactors were coming about, but just public perception, because it was very much a gear up time frame. And I know not necessarily you're working on the weapons side itself, but I was curious to just see even like the testing aspect, how many people were rejecting any kind of nuclear force at all, just being used on any objects. So that definitely shed some light there, and I appreciate going through that. And I guess I'd love to kind of go into it, that you were working for the defense for a while, but then transitioned to, was it the private sector after that, or did you eventually go into teaching?
No, I went into teaching. So I left the defense work. I had the opportunity to take a position at a small college called Carthage College. It's in Kenosha, Wisconsin. And because I was a scientist who run companies, Carthage was looking for somebody to actually begin the first undergraduate program in entrepreneurship and technology business development. They had had a graduate who had done well donate a bunch of money and said, the science students are going to run the world, but they don't know how to do it. You need to teach them how to do it. So, starting in the early 90s, actually mid 90s, we created what was the first undergraduate program in entrepreneurship education. And I also taught physics and astronomy. And as I said, I coached the hockey kids because that was a fun thing to do, and help me interact with the students at a different level. But we started entrepreneurship education with courses. It's what I used to call a mini MBA on steroids, to give students, the core business and career skills that you really need to have. And then students who continued in the program as seniors would do detailed business plan projects with outside customers and technologies. And those students did very, very well because they came out of college actually knowing how businesses work. And they had a lot of great skills, and they've done very, very well. So I'm very proud of them. But we also built a really world-class physics department. When I started at Carthage, we only had one student studying physics and astronomy. We built it to 80.
Really?
Yeah, at a small school. And I had tremendous colleagues to work with, Sean Quashnock and Kevin Crosby, and then later others that joined the department. And it's a tremendous success there to have those students doing this kind of work. And part of it was, we had a lab, we had a shop, we had the entrepreneurship program. I built a program of doing observational astronomy at some of the big observatories out west, so that was interesting to students. And Kevin Crosby started a program with the zero gravity program, NASA's zero gravity program. So we had students actually flying on the zero-G airplane, the parabolic flights where you actually float, doing experiments there. So all these different opportunities were great for the students, and it's still a very successful department. So it's been a model for how physics education can be done. And I've been on a couple of big national panels because of these things. We put out two big reports, one called the Phys 21 report, which is what should physics education look like for the 21st century, and then a report called the EPIC report, which was educating physicists for impactful careers. So I was co-author on the first and the primary author on the second, and those are big national efforts to try to improve science education in the U.S.
Yeah, I'd love to start with you doing the business entrepreneurial program. How do you teach people to have that entrepreneurial mindset? I know you mentioned how they would talk with different business owners and create a business plan, but when you're an entrepreneur, you're creating something brand new. How do you teach people to be different from others? Because there's a lot of people might have the same idea as someone else. How do you teach them to be a little bit different or solve a problem that not many people know?
So a couple of things. The first is that that entrepreneurial mindset, and I think I'm glad you used that terminology because that's really what's appropriate, applies everywhere. It doesn't matter whether you're starting something from scratch or you're working for General Motors, right? There are things that have to be developed. And the biggest difference, if you do it on your own, you're looking for some form of capital to finance it. If you work for a company, the company is the source of money to finance it, right? But the basic principles still apply. In other words, as you said, you have to be solving a problem. The problem has to be something people are willing to pay for. You have to have a solution that is competitive enough versus others who may be trying to solve it or approach it. So in our program, there are a bunch of things that we did, and I've done workshops. I've actually done workshops all over the world on how to do this stuff, but they're actually exercises in creativity. So creativity and innovation, there are things that you can actually do to learn processes for breaking down some of those barriers and coming up with solutions to things. So in our program, we did a couple of different things. Part was just core skill base. I mean, you need to know how to manage money. You need to know what some of the legal and standardized things are out there and how they work. You need to be able to put a plan together that makes sense. You need to know how to manage people. All these core skills that you need. But then there is, as you said, this aspect of, well, how do you identify a problem and how do you solve that problem? And understanding product life cycle is an important part of that. So we talk a lot about product life cycle. And then what we did was a number of exercises. So there's a thing called lateral thinking, and there's actually a process for how you put a team together and develop a massive list of ideas. How are we going to do X, or what are the opportunities for, or how else could we use this? And then what the different principles are for how you down select from that massive list to things that you could actually pursue. There's actually a process for doing that. And we don't have time today to go into it, but there are ways, there's a structure for doing that. So we can teach people how to do it. So then how do we have students practice this? One way was I'd break the class down into groups and I'd give each of them a patent. I just go to the patent database and pick up some technologies and hand out these technologies. Say, okay, for the next period of time, your job is to come up with every single product you can think of that would use this technology. I want you to think as the craziest ideas you can come up with and what you can do. And I give them some of the examples when we talk about intellectual property. I'll show them there are all sorts of things that are patented that are out there that never make it to market. And you go, well, why? And you look at some of the ideas and you go, well, that's not really going to be interesting to anybody, right? Okay. And then other things you're like, well, that was a good idea. Why did it not make it to market? So having them go through that process of saying, here's a technology. You're working for a company and you're working on this technology. You should be thinking about, okay, what are all the other things I could do with it, right?
Yeah.
And that's a big part of that process. So you look at something and you say, I don't know what an example would be here. You come up with some kind of wire that's needed in some kind of circuit thing. When you say, well, wait a minute, why am I using that kind of wire? Well, it's a very stiff wire. Okay, where else could you use stiff wires? If we develop it for this, maybe we could do this, and this with it, right? So it's having that mindset of what are all the things that are out there. Other ways you can do things. We were doing a completely separate project, not related to the program. We're developing some demonstrations, some optics demonstrations. I literally sent the kids to the supermarket with a laser pointer, and I said, go find liquids where if you put the laser pointer through it, you can see the beam. So we could use it as a way to show where lasers are going. So it's like, okay, go be inventive, see what you can find. So different activities like that can help in that process.
I think that's a really good mindset and process to have, because I've talked to professors recently and they all kind of say the same thing of they're teaching kids to be critical thinkers and try to maybe not necessarily get them ready for the career force, but teach them to have that ability to think. But I really like your approach where you're giving them hands-on experience and application-based things, because I think that just goes so much further, because you're teaching them to critically think and also be able to handle different maybe not situations, but think creatively. And I had a marketing teacher in high school, and she gave pretty much groups in class a bucket of items, and you had to choose one. And I had an avocado cutter where you had, it was like a green cutting utensil, but you had to think about a different solution for it. What else could it be used for? And we were thinking of like sand castles and all these different kind of other objects. And that's what I appreciate about the way you were teaching is that is much more that creative aspect. And did you find that more people were left-brained or right-brained? Because one side people have much more of creative thinking, other sides very much more critical thinking logically. Did you find that in your entrepreneur program, one you could notice one side being used more than the other? Because it sounds like you were teaching people to just be more creative, so it could have been a little bit of both.
Yeah, I mean, I don't think I ever broke anything down into particular categories or abilities. I think we just went ahead with, the skill and experience base to try to prepare the students. And certainly, I think you'd find this in any population in any area. You're going to have a spectrum of capabilities and a spectrum of motivations. There are students who just glom onto something and they just throw themselves at it. And then there are others that you have to, not quite drag kicking and screaming, but you have to push to do things. So you're just going to have that in any group of people doing any activity, right?
Oh
You're
yeah,
going to have the gung ho's, and you're going to have the others who you're trying to motivate. So we certainly saw that over the
which I
years in the
gotta
program.
say, with the business entrepreneur program that you were teaching for a really long time, and then transitioning over to the building the physics program, it probably worked great to have that mindset, build that mindset, especially throughout your working career, to then build this program from the ground up.
Mhm.
And you said you had one person that was studying physics at Carthage at the time.
Right,
So how do
exactly.
you even build a program to get 80 people in a sense? Because if it's not a widely known program, it's got to be tough to recruit members and even faculty to come into it.
hmm So, firstly, at the time, we had a president who was really rebuilding the college and building these departments. And he made the commitment. He said, we're going to have 3 people teaching physics, period, and we're going to hire them and we're going to have that. And I came along really for the entrepreneurship program, but I happened to be a physicist, so he counted me as one of the physics people. But we had, a couple other people there, and um, as you said, I'm a builder type person. I mean, it's one reason I was successful at SAI. At SAI, we were the world's largest employee-owned company. The employees owned the company. It was not a
Wow.
public company, and so there was
And what does
a
that
general
mean for?
that the goal was that you should make more money growing the company stock than you make in your salary. The goal of
Gotcha.
everybody was to build the company. And we were very entrepreneurial. Every division was a separate company. You did your own hiring, your own firing, your own HR, your own business development, and it was a sink or swim
Your
environment.
own HR.
That's right. That's right. I had to
Wow.
hire people to take care of stuff. Now, yes, there were corporate people who handled a lot of these things, but you were responsible for all that, which is different than if you work for a typical company where you're responsible for your product line and other people take care of everything else. You had to do it within your division. Um, and you can argue, is this a great way to do things? I mean, we used to joke that every day you came in and your name was still on the door, you were good for 2 weeks. The worst they can do is fire me today and give me 2 weeks notice, right? So you were there trying to build every single day. And that suited my character very well. There are many people it would not suit. There are a lot of people who say, just tell me what to do and I'll do it and I'll do a great job of it. They're great employees. They would not fit in our company, right? Because
Hmm.
you can't be just a tell me, it's like, no, you got to figure out what to do and you got to get it done because that's the character. So working for SAI, which frankly I stumbled into, I got invited to an interview and it seemed like a cool place and they made me a good offer. So I took the job, but it turned out to fit my character extremely well. So then moving from that into academia, normally in academia, a person like me would die because academics do not think that way. And academia is the slowest evolving industry in the world. That's one reason that colleges are closing left and right now. Academia is in big trouble because they don't adapt. But I was brought in to create a whole new program and to help build a department and we were given pretty much free reign to do that. And that was, again, suited my character. It's like, okay, I'm going to create this. I'm going to go pound the pavement, raise some money, recruit some students, get some businesses. And we did the same thing in physics, which is, we decided to build a lab space and throw in a bunch of couches and stuff where kids could hang out. all of a sudden kids start hanging out and they start seeing experiments getting done and talking to people, and they're like, oh, this is actually kind of cool. And so you get a couple of kids, and then their friends come and hang out with them and discover it's kind of cool. And over time,
Hmm.
you start building a program. So that space was important. The courses we did were important. Building the research opportunities. Hey, this is a fun thing. Let's fly to Arizona and go play with some telescopes. That was exciting to students. I do that, and so you put
Yeah,
those
you said
pieces
you
together.
started a program.
Mhm.
Yeah, you said you started a program, right, where you guys would go do different astronomy events out west, correct?
Right. Yeah, exactly.
What did that
Using big
entail?
research telescopes. Well, it's interesting. So I'll give you a little piece of implicit personal advice here. You've heard the phrase, it's not what you know, it's who you know. You've heard that
Yeah.
phrase? Yeah, that's not correct. It's not what you know, it's who knows you.
Mm.
Okay? So you can go around and say, you've been doing these podcasts. I know a whole bunch of people, but the job isn't for you to know them; it's for them to know you, right? If somebody famous, if somebody at NBC News knew you, that's much more important than you knowing somebody at NBC News, right? In terms of actually getting someplace. So, because I'd had a research career and because I'd been out in various places, and been involved in a lot of projects, there were people who knew who I was. When I called them up and I say, "Hey, here's something I want to do," they're like, "Oh yeah, let's see if we can do that for you." And so we were able to get some observing
Wow.
time initially out in Arizona. And that means, well, firstly, you get your first run, you take some students there, you do something, but while you're there, you get some other more people to know you. So when you say, the next time I want to come out, hey, can I, do something with your project? And you start building that. And that's one of the most entrepreneurial mindset elements is you have to get out and you have to get people to know you. You have to
Yeah,
become known as the go-to person for whatever it is you're doing. And
I've
that's
never heard
key.
that before. I've never heard a phrase like that before of they have to know you versus just you knowing them. Because
Right,
the is it more of like the impression that you make on them, so then they can take your name out to wherever? Because now, like you said, you had that opportunity to call whoever, and they said, "Let me see what I can do for you," because you made that impression on them. They know your work, and
right,
now you can kind of do whatever.
right,
So
exactly.
what did these
So
events
that's,
entail then?
so that's something you should be thinking about in terms of this work that you're doing now is like, how can I get this to be known? How can I get enough people to see what I'm doing so that when I contact them, they go, "Oh yeah, I've seen you. I know your stuff." That's the step, right? And that's the most entrepreneurial thing is you have to get out there and you have to do the work and you have to pound the pavement to get that visibility.
100%.
It means going to meetings, it means going to trade shows, it means attending events so that you become visible.
100%. And when you go to these astronomy events, were you bringing students to them and you would go
Mhm.
to a lab and then you would do a project? Or is it observing the planets, the stars, talking about what you've been learning in class?
No, it was doing research projects using large research telescopes at our major observatories, and students came with me and we teach them how to run the telescopes and how to take the data, how to analyze the data, how to publish and present that. That's what we did. So students would come out with me. We'd be up all night running the telescope. They'd come back, analyze the data. We'd take them to conferences where they could present that. And they invariably ended up with internships or jobs because they did that work.
Yeah, application pieces are just so important. And what kind of data are you guys collecting? Because I
So uh, it depended. I mean, there were a couple of different projects we worked on. One of the projects we did was studying asteroids. So asteroids, big irregular rocks that are tumbling through space. So if you measure how bright they are, you keep taking images of them. and you measure their brightness as they move through space, you can figure out what their shapes are. And the other thing is, if you do that and measure it in different colors, you can determine what they're made out of. So one of the things that we were doing was studying different asteroids and saying, okay, can we figure out certain characteristics about their shape and how they're put together by taking these images through different filters, measuring the brightnesses, then building a model, big spreadsheet model, you put all this data in, plotting things out and seeing if you can figure that out. So that was one of the big projects that we did. And,
Holy cow!
I've got hard drives here. There's tons and tons of data right there. If you want to play with science data, I can put you to work. I don't think you really do that, but I could do
that. I mean, I'm more than happy to just test it out and just see what it's like, because I didn't realize you could tell by how fast they're going, the light they're giving off to determine the shape. In my head, it just can't comprehend how that works.
Well, I'll give you an example. Let me give you an example. Okay. This is a Coke bottle, right? Right? Mm-hmm. Now, you can see it in 3 dimensions, right? But imagine you can't. Imagine if you only saw the light reflected off of it. So in this direction, the big area, it's very bright, right? What happens if you see it in that direction? That's a small area. It's going to be dim.
Yeah.
Now,
okay.
As it rotates, we can measure how bright and how dim it gets, right? So the fact is that, this is very long and thin. We can determine that it's long and thin because while it tumbles, sometimes it gets pretty dim and sometimes it gets pretty bright. If you had something that was more like this, right? There's your dim, there's your bright. But if it's tumbling in a different direction like that, right, its brightness will change differently. So by measuring the brightness, slowly but surely, which takes many, many hours, sometimes several days of taking data, you can start to figure those things out.
And what does that
science
do?
Is cool. Science is cool. You can figure these things out. So what's the purpose of doing that?
Yeah. Are you guys testing to see maybe what kind of elements or minerals that are on these asteroids, or the trajectory of where they're going?
All of the above. I mean, there's a lot of stuff out in the universe that's worth studying because we don't know about it, right? And you don't know what you're going to find. So you go out there and you try these things. You say, okay, is there a way we can identify what these population of objects is, where they came from, what they're made out of, where they're going, all of that. So that's part of what research is, right? You go out there and you say, okay, let's look at these things, see if we can understand them.
Yeah, I guess because we don't know what's out there, it makes a bigger purpose to go research it. But there's also studies that show that we don't know much about the ocean. And I feel like we spend a lot of time trying to figure out what's out in space. How come a lot of physicists don't maybe necessarily focus on what's underneath us on Earth itself?
That's a good question. I mean, there's a huge range of things that can be studied and worked on, right? What's in the ocean is one of the, I mean, we're still finding new species of things on the planet every day that we didn't know about. So there's every reason to pursue every possible avenue of research. Why do certain ones get more attention than others? That's politics and sociology. That's not science, right? It's like,
gotcha.
What gets people's attention? What's worth working on? And it's not that there isn't oceanography work going on. There is. It's just not my field, so I can't tell you what's really going on there. I can point you to people for whom that's a specialty. I'm working in the areas that are interesting to me. Which isn't to say that I'm not interested in the ocean, but you can't study everything in detail, right? So that's the scoop there. But I mean, you ask a fundamental question, which is, given limited resources, what should we spend our effort on? And that's a sociology and politics question.
I didn't, and I guess it really is, I guess, more of a political thing, because you hear a lot more about space and the programming, funding, all that stuff towards maybe the NASA programs or SpaceX.
Mhm.
Lockheed Martin, stuff like that, where they're all building rockets to do the next thing out in
Right.
space. But you don't necessarily hear about what's happening in the ocean. And so I guess I should have rephrased that last question to not be how come people aren't studying it as just more why then it's not talked about. So it does go to the political aspects, which is it's so it's so complex to just think about the whole system as a whole of what gets broadcasted when and what's going to be more appealing to viewers.
Right. Right. Yeah.
And
And let's admit, astronomy is sexy. I mean, if you put a telescope out on a corner, people want to look through it. And as a matter of fact, I mean, that's the basis of this public science program that I've been doing for the last almost 15 years, is the fact that astronomy, both, it's the science of everything, right? It's the study of the universe. So there's absolutely everything is really part of astronomy. But the other thing is it's
yeah,
sexy. If I put a telescope out, it gives me an entree to talk to people. Whereas if I just sit there with a bowl full of fish, yeah, some people may come by, but there's something very attractive about having a telescope, and we use that. You know,
yeah,
it's marketing, right?
100%.
How do you get people interested?
And I have to ask you, do you think it's possible to become a multiplanetary species? And do you also think there's other life that is out there in the galaxy?
So, okay, fundamentally, let's talk about the life thing first. The basic chemistry that makes life possible, which is driven by carbon, oxygen, hydrogen, and a couple of other things, is all through the universe. Stars are busy making more carbon and oxygen than anything else besides helium. And so the chemistry to make life is everywhere. And the universe is really big, right? There's a trillion galaxies. They each have 300 billion stars. Those stars all have planets. And they're all bathed in organic chemistry. So,
Yeah.
from my perspective, I would consider it likely that there's life elsewhere in the universe. On the other hand, I think it's unlikely that you will find any particular kind of life somewhere else in the universe because there are so many different ways to make it, right? There are hundreds of millions of different species of life on this planet alone.
Hmm.
And think about all the species that used to be here that aren't here anymore. Dinosaurs were here for 250 million years. That's way
Yeah.
longer than
And then,
humans have been around, right? Okay.
yeah.
So if you go to another planet and you find life, the chemistry may be similar, but the form may be very different. In fact, I would expect the form to be different, right? Just imagine. Let's go back a couple of hundred years, and you're Darwin, and you're sailing the Earth, and you land in Australia, and you find marsupials, you find kangaroos. There are no kangaroos anywhere else on the planet. They only developed in Australia. Until you got to Australia, you'd never know that there were things like kangaroos. I mean, as far as you know, the animals are all lions and tigers and bears because that's what you see at home. And you come there and you go,
Yeah.
"Holy crap! Look at that thing. What does it look like that?" So if we go to another planet, I'm totally convinced you'll find life somewhere in the universe. Now, whether it's findable or not is another question, right? But I'm totally convinced there's life, but I'm totally convinced it doesn't look like us. It's
I was going
not
to
going to
say,
look like.
like, could, when people, if we ever do find another planet to live on, do you think the people that would be living there and growing food, whatever that may look like, or eating, they would evolve in their own realm? So we breathe oxygen
Well,
here. Maybe over
I mean,
time.
are you asking if we transplanted some number of humans to a different place, what would happen? I mean,
Yeah,
I
because I'm thinking species evolve based on their habitat. That's what animals do. Would the same be the case if we were to, like, a small group of species or of us just went to a different planet? Over time, would we evolve based on the conditions that are present?
well, you have to remember that evolution is driven primarily by the dying off of one population in favor of the survival of another population. Okay, so what you would find is if you had a group of life, whatever flavor it is, and you put it in a different environment, some of that life is going to be better tuned to that environment, and those genetics will continue, and the ones that are less tuned are going to slowly die off, right? Now, the more fundamental question is, are we going to move people to another body? And the answer is probably not, because things are really, really far away. Okay. People don't understand how big space is. Remember, it took 3 days to get 3 people to the moon. And the moon is
Yeah.
only a quarter of a million miles away. And it took a huge rocket to send 3 people. Okay. So imagine trying to send a population of people to another planet. You know, yes, the technology exists. It's a matter of money, right? You build 100,000 Saturn V's and you move 300,000 people. You could do that, but it would not be
Take
very efficient.
billions of dollars.
Trillions of dollars.
Trillions.
And then,
Holy
and
cow.
yeah, because you also have to send all the support. You're not just sending the people. You have to send material to build buildings and stuff. And remember, you're dependent on a lot of other life. I can't just send you with food. I have to send you with things that make food, right?
Yeah.
So
Yeah.
you have to have stuff that's going to grow. So you have to supply all of that. So it's not a simple thing that's going to happen. Certainly not in our lifetime. Now, will there be some form of exploration? Could we send a capsule of people to Mars to explore for a little while? Sure, that's only a matter of money, right? But are we going to move a big population somewhere else? Not happening. Not possible.
No,
Not happening.
definitely
So
not in our lifetimes, for
not
sure.
ever. Not ever.
Not ever.
Not ever. You're not
Because
going to
do you have to
move.
find the exact like hospital planet that mirrors the Earth in a sense, just so people can co-live there with whatever is there?
I mean, the nearest star is 24 trillion miles away. We're not getting there. Period.
Yeah. Gotcha.
It's not happening. So, I mean, we need to take care of this planet. I mean, that's the reason this whole public science program exists that I've been running, is to get people to understand where we came from, how all the life is interconnected, how the whole history of the universe led to us being here, and why we need to take care of what we have. Because if we don't take care of what we have, there's no next thing.
Exactly.
People don't get it.
And I guess, yeah, let's talk about this Mountain of Stars program that you have. It's all about the interactions, about how space and here relate to one another, and how we are using it to, like you said, we have one planet. This is it. Can you talk a little bit about the program and how you teach others about physics and astronomy?
Sure. So, launched this program. We funded it in 2011. We did our first programs in 2012. So we're in the 14th year of programs, 15 years of doing this stuff. And the fundamental idea, as I said before, is to use astronomy to connect people to the biggest of big pictures and how everything is interleaved. So why vision is our dominant sense, and why that connects to how radiation travels through space and through water, and why the moon is a critical part of our existence, because it was a considerable force in getting life out of the ocean and onto land because of creating tides. But the moon was created by a random accident early on in the formation of the solar system. So what does that mean for our existence, right? What does it mean for life somewhere else? What does it mean for the different kinds of life on the planet? Understanding there have been 5 major extinctions, that life has been wiped out on the planet 5 times. The last big one was because of that asteroid that came and took out the dinosaurs. That's a definite space connection, right? If we didn't get hit by that rock, you wouldn't be here, and dinosaurs would still be wandering around very happy. So understanding all those processes is key to getting people to rethink their connection with everything that's around us, to recognize that squirrels are actually more important to the planet than people, right? To understand all the different life forms and where they came from and why they're here, and how that connects to the whole evolution of the universe and the chemistry that space creates, that creates all that organic chemistry that makes life possible. I think those are all really, really interesting topics. And you can be standing out under the stars. I did a program night before last at one of the facilities here where I was just out with a laser pointer pointing out to different stars and talking about why those star temperatures are so important to our existence and why that kind of light makes a difference to why plants can exist and humans can exist. Those connections are very important. And with that, you start to understand how everything here is connected and how everything here is equally valuable. We are not more valuable than another life form. And trying to get that idea out there so that people say, okay, well, wait a minute, I can make choices, right? I can eat local. I can control light pollution. I can not, destroy the local environment. Those things are important conclusions if you have that understanding. So for the first about 10 years of the program until COVID hit, we had the funds to bring in students. So we would have students as interns working in the summers who did a tremendous job of working with the public. And they benefited because they learned this content and they learned how to communicate. Because scientists as a whole are very poor communicators. And we need to change that. Right? Some of us are good in front of an audience. A lot of people are not good in front of an audience. A lot of people are very, totally concentrated on their one area of research as opposed to trying to say, how do all these science things really connect with people? What can we do to get people to do things better? Which I think in this country is a very big problem. People don't, as a whole, large population does not trust science or understand science. They want the results of it. They want their microwave ovens. They want their iPhones. They want their TVs. They want their cars. But then science says, well, here's what I think we should do. And they're like, oh, no, I don't trust you. We have to break that down. I think that's very important.
And that's just because of the way it's communicated?
Because that's the way it's communicated, right? Exactly. So that's a big thing we're working on.
Yeah, which is crazy to think that people who do so much research are scientists that do so much research to advocate for a certain change that people would hesitate to do it. And right. Do you think it even just goes outside the communication of this is something new and change is very difficult to understand? I mean, I'm just thinking about the adoption of electric cars. A lot of people had gas cars, but now electric is slowly being more and more adopted into automobiles. Do you think that also has a factor to play in it? Is that just change is very tough for people?
Change is difficult for people. I mean, that's certainly true. And it depends on the kinds of change you're trying to create. If you're trying to say, okay, we need to change everybody over to electric cars, you also have to realize that there are a lot of environmental implications of changing to electric cars. Electric cars are not green. I got bad news for you. They are currently bulldozing Bolivia and Chile to get lithium to put in the batteries for all these vehicles.
And those batteries don't decompose or anything?
And the batteries don't decompose. So you have to look at a lot of these things in different ways. But, okay, you're obviously a smart dude, because when I mentioned that, you're like, no, wait a minute, I understand that there's a problem here. There's a decomposition problem. There's a recycling problem. But most people don't understand that, right? That's part of this communication thing. It's like, okay, how can people be educated to look at these things? So, for example, there's a really good book called Ecological Intelligence by Dan Goleman, and he talks about all that. And it was a bestseller book. But we need to get more people understanding that. And what are the best ways to communicate it? Well, what you and I are doing today is a good way to do that, right? You can post this up, you can push it out, and there will, I hope, a lot of people watch this. And when they watch it, they're going to go, oh, wait a minute, I want to learn more about this. What's that guy's website again? It's mountainsofstars.org, and hopefully you'll put that in the comments someplace so people will click on it and they'll learn more.
Oh, yeah, definitely.
How many people will do that? I don't know, but if somebody does it and likes it and shares it with their cousin, who shares it with their neighbor, who shares it with their boss or whatever, you got to start a movement somewhere. So I'm doing what I think is my part to try to make this better. And I want to motivate others to do that as well.
Yeah, and I think that's a really important message of what you guys are doing with the Mountains of Stars. And with the science industry always changing and evolving, how do you stay on top of it so then you can convey people the best possible information or messaging that the science community is just trying to get across? Because there is just so much that's out there. And I know
Mhm.
obviously communicating effectively, doing maybe on hands-on examples is always probably huge. How do you stay on top of it?
I think um, I can't stay on top of everything that's happening in all the sciences. I can try to stay as current as I can in the science areas in which I work. A lot of that is reading. You read stuff. I mean, I was just reading the current issue of Physics Today, which is a publication of the American Institute of Physics, which tells you about some of the cutting edge and interesting things that are happening. Um, I look at the news feed each day. I read a lot of books. There's a great book called How to Build a Habitable Planet by a guy named Langmuir from Columbia. It's linked on our website. But it went through all the science from the Big Bang to present day. And it's like, I read that, and there were so many connections. It's like, oh, now I understand these connections. And look, I'm a professional scientist, and until I studied that, which is in the last 10 years, I'm like, oh, yeah, of course those things are connected. But I'd never thought about that before. So I think
Yeah.
the key thing is to just keep reading and listening and paying attention to things. I even though I'm quote retired as a professional scientist, I still attend the big astronomy conference once a year. And a lot of it's just walking around and looking at all the posters like, okay, who's working on this? Oh, that's interesting. I should know a little bit more about this or that. And I make that effort. So I read things, I go to the meeting, I try to learn as much as I can in the areas in which I'm working. I can't know a lot about lots of other fields. I know something about other fields. I try to stay up with them, but certainly I'm not expert in those other areas because there are enough hours in the day. But I'll spend as many hours as I can to be as good as I can in what I do.
Yeah. And that's what I was trying to get across is just because you can be a professional or expert in a certain field doesn't mean that there's not always something to learn and continue to develop and
Right.
grow. And that just goes for anyone out there is that regardless if you're in a field, there's always going to be the next big thing that comes out. And long past us, there'll be another very big thing or several that come out. And so, Doug, I really do appreciate you being on the show today. It was great to hear from you. And I'm sure it'll connect with a lot of people. And I'll definitely send a link so everyone can look at the Mountains of Stars.
That's great. Well, thank you very much for the chance to talk about this. It's great to connect with you. And congrats on putting out all these recordings that you do with all sorts of people. The more of that we do, the more education you're providing. Some of that education to the general public. You know, you're on the supply side of that. That's really terrific. Keep that up. And if you would like links to lots of other interesting people, I'd be happy to do that. And the more of this you do, the better, and the more widely watched and listened to, the more impact you'll have. So congrats and keep it up.
And no, I appreciate it, Doug. Just last comment on that is it made me think about something. Is earlier you said that the education life is one of the slowest evolving things, and I am hoping, based kind of off that note, is that these episodes kind of give people an idea of what it's like in the workforce, what it's like to be out there, because it is the workforce is always continuing to evolve, and
Mm-hmm.
it's very hard to get that information to school. So if this is that step out there, then I 100% will do it 10 times over.
Great. Well, thanks. Keep it up. You're doing great stuff.
Thanks, Doug.
All right. You take care.
Hey, everyone. Want to take a quick second and say thank you to whoever listened to the episode today. I really do appreciate it, and it means a lot. If you did like the episode, make sure to give it a like or 5-star rating depending on what platform you are listening to. And if you really want to support the show, check out our website or Patreon link below. Thank you, and I'll catch you in the next episode.